Hey everyone, welcome! I am absolutely thrilled to have you here for this explainer. Today, we are conquering Chapter 3 from your Class 10 Mathematics textbook, Pair of Linear Equations in Two Variables. Now, if algebra has ever felt like a terrifying alphabet soup to you, I want you to just take a deep breath. We are going to turn those scary X's and Y's into totally manageable, powerful tools that you can use to solve actual real-world puzzles. Let's make sense of this together.
Here is our quick roadmap for today. We're going to start with the algebra of real life, then move into graphing equations, discover the magic of ratios, learn the substitution method, master the elimination method, and finally wrap up with a summary and some exercises.
All right, let's jump straight into Section 1, the algebra of real life.
Picture a girl named Akila visiting a local village fair. We have two very specific clues about her day. Clue number 1, the number of times she played hoopla is exactly half the number of rides she took on the giant wheel. Okay. Clue number 2, each ride cost 3 rupees, each hoopla game costs 4 rupees, and she spent a total of 20 rupees. So, if we say the rides are X and hoopla is Y, that first clue translates to Y equals 1/2 X. The second clue becomes 3X plus 4Y equals 20. But here's the big question. How do we find the exact values of X and Y without just sitting there randomly guessing numbers all day?
Well, what we just created for Akila is officially called a pair of linear equations in two variables. Now, I know looking at this general form on the screen, a1x plus b1y plus c1 equals 0, it looks incredibly intimidating. But stick with me. The a, b, and c, those are literally just real numbers. And those little 1s and 2s at the bottom, they're just tags so we can tell equation 1 apart from equation 2. The only strict rule here is that a and b cannot both be 0 at the exact same time. Together, these two equations are basically the lock and the key to solving our puzzle.
Let's move on to Section 2, graphing our equations.
Back in Class 9, you probably remember learning that a single linear equation forms a straight line on a graph. But when you plot a pair of linear equations, like Akila's, that's when the magic really happens. Notice how these two lines cross like a physical intersection at exactly one single point? That's the coordinate 4, 2. That single meeting point means X is exactly 4 and Y is exactly 2. So Akila took 4 rides and played hoopla 2 times. We call this a unique solution, and equations that do this are known as a consistent pair.
But wait, lines don't always just cross once. Sometimes, one equation is actually a cleverly disguised version of the other, like if you just multiplied an entire equation by 2. When you plot them, they overlap completely. They are coincident lines. Because every single point on one line touches the other line, they share all their solutions, meaning there are infinitely many solutions. We call this a dependent, but consistent pair.
And then there is a third possibility. What if our equations are like two parallel train tracks? They just run perfectly alongside each other, forever, without ever crossing. Since a solution is literally an intersection point, and these never intersect, they have absolutely zero common ground, no solution at all. We call this an inconsistent pair.
Okay, Section 3, the magic of ratios. Time for a math cheat code.
Let's be real, graphing every single problem takes way too much time in an exam. So here is a brilliant cheat code for you. Just by comparing the ratios of the numbers sitting right in front of your variables, your A's, B's, and C's, you can instantly predict the outcome. If the first two ratios don't match, boom, the lines intersect. Unique solution. If all three ratios are perfectly identical, the lines are basically twins. They coincide for infinite solutions. And if the first two match but the third one fails, parallel lines, no solution. Doing this quick ratio check is a massive time saver.
Moving right along to Section 4, solving by substitution.
So what if your answer involves some really messy fractions or decimals? Graphs just aren't accurate enough for that. We need algebra. Our first tool here is the substitution method. Think of it like a logical loop. Step 1. Isolate one suspect, let's say X, so the equation literally reads X equals something. Step 2. Take that disguise and plug it directly into the second equation. Step 3. Magic. You now have a super simple equation with only Y's in it. Go ahead and solve it. And finally, Step 4. Take that exact number you just found for Y and substitute it right back into Step 1 to effortlessly find X. Which brings us to Section 5, solving by elimination.
Now, substitution is a great tool, but honestly, constantly isolating variables can leave you tangled up in annoying fractions. So let's look at a much faster trick, the elimination method. This is all about balancing the scales to completely wipe a variable out of the game. Step 1. Multiply your equations by specific numbers so that the coefficients of either x or y perfectly match up. Step 2. Add or subtract the equations straight down. Because the numbers match, that variable just drops to 0. It's eliminated. Step 3. Solve that incredibly simple one-variable equation that gets left behind. Step 4. Plug that answer back into either original equation to find your eliminated suspect. I promise, it is deeply satisfying once you get the hang of it.
Now, what if you took those exact elimination steps and applied them to the pure general form? Just using the letters A, B, and C instead of actual numbers? Well, if you do this carefully, you actually derive this massive, complex formula directly for x and y. If you ever come across a crazy formula like this in your studies, seriously, don't panic. It's not dark magic. It is literally just the elimination method done with letters. To me, it just proves how beautifully interconnected all of algebra really is.
All right, let's bring it all together in Section 6, Chapter Summary and Exercises.
We've built up a fantastic toolbox today, so let's actually crack a classic textbook exercise together. Imagine a cyclic quadrilateral where the angles aren't numbers but algebraic expressions. To solve this, you just need to combine your Class 9 geometry with your Class 10 algebra. Do you remember the geometric rule? Opposite angles of a cyclic quadrilateral always add up to 180 degrees. So angle A plus angle C equals 180. Bam, that's equation 1. Angle B plus angle D equals 180. There's equation 2. You now have a perfect pair of linear equations. Choose your favorite weapon, substitution or elimination, and solve it. This perfectly proves how algebra is really just the engine that drives geometry.
Let's quickly recap your new algebraic superpowers. You now know the general form. Graphically, you know that lines can intersect, coincide, or run parallel. You know that awesome ratio shortcut to instantly predict those outcomes without graphing. And you've mastered substitution and elimination to hunt down those exact coordinates algebraically. But above all, I hope you've learned that word problems are just translations. You are simply finding the exact point where two real-world conditions perfectly match up.
Because at the end of the day, these equations aren't just some dry textbook theory. They are the underlying code of everyday life decisions. The next time you try to maximize a budget for a party, or maybe calculate speed and distance for a family road trip, look closely. Ask yourself, what are my two unknown variables? And what are my two clues? The math is hiding right there in plain sight. Can you spot the hidden pair of linear equations waiting to be solved in your own life? Keep practicing, stay curious, and I'll catch you in the next explainer.